From the Ukrainian coastline, a small group of drones lifts into the night. Their destination lies across the Black Sea, inside Russian-controlled Crimea, where layered air defenses guard airfields, radar stations, and patrol routes. These drones are cheap, disposable, never meant to return. Russian sensors begin to search the horizon. Missile crews move into position. Patrol boats cut through the water. Attack helicopters spool their rotors. But the drones do not fly high. They fly so low that radar struggles to see them. What happens next exposes a weakness inside one of the most heavily defended coastlines on Earth. Ukrainian launch and mission planning. Night presses down on the Ukrainian coastline, thick and lightless, broken only by narrow beams of red-filtered lamps and the quiet movement of men along a concealed launch site. The shoreline looks empty from a distance. In reality, it is alive with preparation. Technicians kneel beside long, narrow airframes resting on low transport cradles. Composite skins reflect almost nothing. No markings, no serial numbers, nothing that needs to be recovered later. Weeks earlier, Ukrainian intelligence officers begin shaping this moment. Commercial satellite imagery is layered with military-grade reconnaissance. Patterns emerge: aircraft parking layouts, radar mast positions, vehicle tracks that reveal patrol routes, heat signatures from generator shelters. Repeated observations show which Crimean airbase hosts transport aircraft on a regular cycle, and which revetments remain occupied through the night. Analysts notice something else: a corridor over water where radar coverage appears inconsistent, a thin seam between overlapping surveillance zones. That seam becomes the highway. Target selection is not about symbolism. It is about vulnerability. The chosen airfield sits close enough to the coast to be reached by small engines, but far enough inland that defenders assume warning time exists. Transport aircraft parked in open dispersal areas become priority targets. They are large, thin-skinned, difficult to rapidly relocate. Destroying even one forces logistical disruption across an entire sector. Planners do not design a single drone for this mission. They design a behavior. Multiple aircraft will launch together, not in formation, not in a tight swarm. Each drone follows its own slightly offset route, separated by hundreds of meters, sometimes kilometers. If one is destroyed, the others continue unaffected. If several are detected, defenders cannot know how many remain. The drones themselves are built for one purpose: reach the target. A small piston engine drives a rear-mounted pusher propeller, chosen for efficiency rather than speed. The airframe is built from lightweight composites that absorb radar energy instead of reflecting it cleanly. Wings are long and thin, optimized for lift at very low altitude. Fuel tanks dominate internal volume. Range matters more than payload. In the nose sits a modest warhead, shaped to direct its explosive force forward. It is not designed to level buildings. It is designed to rupture aluminum skin, ignite fuel vapors, and start fires that grow. Navigation is simple but resilient. A satellite receiver provides position updates. An inertial measurement unit tracks movement when signals degrade. A pre-programmed flight path exists inside memory, broken into waypoints that do not require continuous operator control. Altitude is the core of the entire concept. These drones are instructed to fly just meters above the sea surface. At this height, radar energy skims over them or reflects into the water. Waves become clutter. White caps become noise. The drone does not need to be invisible. It only needs to be difficult. Launch begins quietly. One by one, engines cough, then settle into steady, low RPM hums. Airframes roll forward. Wheels leave sand. Each drone lifts, stabilizes, and immediately descends until its shadow merges with the dark water below. No radio chatter follows. The aircraft turn toward Crimea and disappear into the night, already committed to a path that does not include coming home. First radar detection and TOR M2 engagement. Far out over the Black Sea, Russian coastal surveillance radars continue their slow mechanical rotation. Antenna arrays sweep through darkness, sending electromagnetic pulses into humid air and receiving only fragments in return. Most echoes are dismissed instantly. Rolling waves, spray lifted by wind, thermal distortions hugging the surface. The software is designed to filter this noise automatically. Then a faint contact appears. Not a solid track, not a clean return. A weak, unstable reflection that exists for barely a second before dissolving back into clutter. Moments later, it appears again, slightly closer. A second flicker joins it, then a third. Individually, none of these signatures look like aircraft. They are too small, too inconsistent. Their radar cross-sections resemble floating debris more than flying machines, but the movement pattern is wrong for debris. The points are drifting inland, maintaining spacing, maintaining speed. The radar system flags the cluster and forwards the data to a nearby TOR M2 air defense battery. Inside the TOR command vehicle, processors begin building tentative tracks. The system's phased array engagement radar slews toward the bearing, switching from wide-area search mode into focused tracking. A narrow beam punches through the night, refining the picture. 6 small objects emerge. They fly extremely low, barely meters above the water. Their composite airframes absorb much of the radar energy instead of reflecting it. There are no large metal surfaces, no rotating turbine blades, no vertical stabilizers that normally create strong returns. To the radar, they look like faint smudges sliding across a noisy background. But faint does not mean invisible. The TOR's computer assigns threat numbers. Engagement priority rises. The system rotates its launcher toward the incoming tracks. A missile is selected. Compressed gas ejects a 9M331 interceptor vertically from its tube. A split second later, the rocket motor ignites, throwing the missile forward at supersonic speed. Guidance commands stream from the fire control radar, steering the interceptor toward the leading contact. The missile's proximity fuse begins searching for a target large enough to justify detonation. That is where physics intervenes. The drones are small. Their reflective surface area is tiny. Their shapes scatter radar energy instead of bouncing it straight back. The fuse struggles to recognize a valid signature. It is tuned for jets, helicopters, cruise missiles, not lightweight composite airframes barely wider than a motorcycle. The missile races past one drone, missing by meters. Fragments from the near miss pepper a second drone. Shrapnel tears through its skin, punching holes in control surfaces and wiring. The drone wobbles violently but does not disintegrate. Its engine keeps running. Its guidance system keeps working. 5 drones continue forward. The TOR battery launches again. Another missile screams into the darkness, and the drones do not turn back. Decoy drone and radar saturation. As the first drone begins its climb, the subtle hum of its engine barely registers over the Black Sea's rolling waves. Every meter upward transforms it from a low observable dot into a dramatically larger radar return. The air defense computer sees a sudden spike. Its algorithms interpret the rapid vertical movement and expanding signature as a major threat, most likely a fighter jet or incoming missile. Soviet-era programming prioritizes the largest, fastest climbing contact first. The decision is automatic, immediate, and unyielding. The lead drone has become the perfect decoy. From the TOR M2 battery, the command system allocates multiple missiles to intercept. Calculations are lightning fast. Trajectory, speed, wind, altitude, and predicted evasive maneuvers. A 9M331 missile launches, screaming into the night, followed closely by a second, and then a third. Each missile is guided by continuous radar commands, tracking the climbing drone with precision that would have been devastating if it were a conventional target. Yet the drone's composite construction scatters radar waves. Its evasive micro-adjustments in flight confuse the missile's proximity fuses. Explosions occur meters behind, spraying fragments that would have shredded a traditional airframe. Meanwhile, the remaining drones respond exactly as planned. They descend toward the sea, dropping into a narrow altitude corridor that keeps them below the radar's optimal engagement envelope. Low-altitude flight over water reduces radar returns drastically. The surface reflects radar waves in ways that obscure their tiny forms. The operators controlling the drones are executing a pre-programmed plan that exploits these limitations, using wave geometry, clutter, and Doppler effects to minimize detection. The Soviet-era threat prioritization logic becomes a double-edged sword. The system is excellent at identifying large, fast, vertically moving targets, but less effective against multiple low-speed, low-observable aircraft approaching simultaneously. By focusing on the climbing decoy, the air defense battery diverts attention and firepower away from the smaller, true threats. Each missile expended on the decoy represents a momentary window for the remaining drones to advance unchallenged. As the decoy is battered by missile fragments, it continues its climb just long enough to keep the system fixated, before veering off toward open water. Its sacrifice is not wasted. The formation split ensures that all other drones bypass the engagement zone undetected, slipping past a multi-layered air defense network designed to destroy targets many times larger, faster, and more resilient. The deception is complete. Raptor patrol boat intercept. Near offshore platform, a dark silhouette floats motionless beside the skeletal remains of an offshore gas platform. Rusted steel legs rise 30 meters above the water, casting jagged shadows across the surface. The Russian Raptor-class patrol boat keeps its engines cold, drifting quietly in the platform's blind zone. From a distance, it looks abandoned. In reality, it is waiting. Inside the cabin, operators stare into glowing screens. One display shows radar contacts from higher command. Another shows a thermal image of the surrounding sea. Then faint white smears appear on the thermal feed, not reflections, not wave crests. Heat. Small gasoline engines burn hotter than the ocean by nearly 200 degrees. Against 15-degree water, the drones shine like embers. The thermal sensor begins auto-tracking, drawing boxes around 4 approaching points. The boat's commander does not hesitate. The remote weapon station rotates forward. Its heavy machine gun stabilizes on electric servos, compensating for the boat's gentle roll. The ballistic computer begins calculating lead angles, factoring in target speed, crosswind, and distance. At 1,800 meters, the first burst fires. 14.5-millimeter rounds streak across the darkness, tracer lines forming curved orange arcs. Each bullet is thumb-sized, heavy enough to punch through light armor. It walks fire across the lead drone's path. Rounds punch through composite skin. Pieces of foam and carbon fiber tear loose and vanish into the sea. The drone shudders but stays airborne. There is little inside to destroy. No pilot, no cockpit, just a small engine, wiring harnesses, control servos, and a warhead in the nose. The drone responds by climbing sharply. The sudden vertical movement forces the gun's elevation motors to chase. The mount can only raise its barrel to about 60 degrees. As the drone climbs overhead, the angle increases beyond that limit. The gunner can still see the target. He can still track it, but he cannot physically point the gun high enough to shoot. The Raptor's engines roar to life. The boat accelerates hard, slamming across the waves at nearly 50 knots. Every impact sends shock through the hull. The stabilized mount struggles to keep its aim steady as the deck repeatedly leaves the water. 3 remaining drones split directions. 1 climbs, 2 dive lower, hugging the wave tops. The gunner is forced to choose. He slews toward the climbing target, hoping to finish it before it escapes overhead. In doing so, the 2 low-flying drones slip outside his immediate firing arc. The boat attempts to turn. At high speed, physics wins. The Raptor's turning radius stretches hundreds of meters. It cannot pivot fast enough to bring its gun back onto the low targets. The 2 drones flash past the patrol boat, so low that spray kicks up behind them. They are gone. The ambush has failed, and the coast lies open. High-speed chase and Ka-52 helicopter scramble. The 2 remaining drones slice through the pre-dawn haze, skimming the Black Sea at 30 meters above the waves. Behind them, the Raptor patrol boat struggles to maintain pursuit. Even at full throttle, it cannot match the agility or speed of aircraft designed to dart between radar cones and outrun mechanical retaliation. Its hull pounds against each swell, engines screaming, the stabilized gun mount jerking violently with every impact. The drones are already beyond its effective engagement range, leaving the crew frustrated, eyes fixed on distant heat signatures fading into the horizon. High Command in Sevastopol registers the intrusion. Minutes earlier, operators had tracked the initial incursion on coastal radar, but the low-altitude sea-skimming flight path and small radar cross-section of the drones make them difficult to intercept from ships alone. A rapid decision is made. A Ka-52 Alligator attack helicopter scrambles from a forward patrol station 30 kilometers east, its twin coaxial rotors spinning violently as it lifts off. The helicopter's Arbalete 52 radar activates immediately, sweeping a wide sector over the Black Sea. Thermal and optical sensors complement the radar, providing multiple layers of tracking. The system locks onto the drone's faint heat signatures, engines burning at nearly 200 degrees Celsius against the cold morning water. The targeting computer begins calculating lead angles, factoring in the drone's speed, course changes, and altitude fluctuations. The pilot selects a Veer missile, originally designed for armored targets on land. The missile, accelerated by a solid fuel motor, launches in a plume of fire and smoke. It is guided by a laser beam projected from the Ka-52, which the missile tail sensor tracks like a train on invisible rails. Yet the drones do not present conventional targets. Their small composite frames reflect minimal heat and radar energy. The missile seeker struggles to maintain lock, needing continuous corrections to remain on target, while the drone executes sudden vertical climbs and lateral jinks. Despite these challenges, one missile finds purchase. It detonates with precise timing, striking the lead drone and tearing its fuselage apart. Shards of carbon fiber and wiring spray across the surface of the water, steam rising where hot engines meet the cold sea. Yet the other drones continue, weaving through the air, exploiting gaps in the helicopter's firing solutions, their pre-programmed evasive maneuvers, allowing them to skirt the edge of detection. The Ka-52 banks hard, attempting to cover the chase, but every evasive movement by the drones forces the pilot to constantly recalculate. The aircraft's engines roar, pushing the helicopter to its limits, while the clock ticks. Each second matters. Each maneuver must be precise. Even now, the drones maintain speed, altitude and course with uncanny precision, their low signatures and rapid changes in position, keeping them just out of reach. The chase intensifies, a deadly ballet of man, machine, and mathematics over the open sea. Electronic warfare and autonomous navigation. The Ka-52's onboard electronic warfare suite switches from passive listening to active attack. Antennas embedded along the helicopter's fuselage begin pumping out concentrated radio frequency noise. The output is not subtle. Hundreds of watts of energy flood the spectrum used by commercial satellite navigation receivers, civilian data links, and line-of-sight control radios. Every frequency band the drones might rely on is saturated. From the Ukrainian control station far across the water, video feeds freeze, telemetry numbers stop updating, command inputs vanish into static. For a brief moment, the drones are alone, but they were built for this moment. Inside each airframe, a small flight computer detects the sudden loss of external command signals. A timer starts. When no valid uplink is restored within milliseconds, the software executes its contingency branch. Autonomous mode engages. Control authority transfers from remote operator to onboard navigation logic. The drone no longer listens outward. It turns inward, trusting data stored in memory and measurements coming from its own sensors. A tiny inertial measurement unit buried inside the fuselage begins doing constant math. Gyroscopes track rotation. Accelerometers sense movement in 3 axes. Every tiny change in direction, every vibration from the engine, is integrated into a continuously updated estimate of position and orientation. The drone also continues sampling GPS signals, but it no longer depends on them. If satellite data becomes corrupted by jamming, the inertial system bridges the gap, keeping the aircraft on its predicted course long enough to reach its next waypoint. Each drone carries a preloaded route, not a straight line. A chain of geographic coordinates that bends around known radar sites, skirts expected patrol zones, and funnels the aircraft through terrain and sea clutter corridors where detection probability is lowest. As autonomous mode activates, the formation performs its next programmed behavior. They split altitude. One drone climbs to nearly 200 meters, another stabilizes around 80. The third drops to less than 10 meters above the water, skimming so low that its shadow briefly merges with the waves beneath it. This vertical separation forces defenders to solve 3 different engagement problems simultaneously. High-altitude targets trigger long-range radar and missile solutions. Mid-altitude targets fall into helicopter and gun-based engagement zones. Ultra-low targets drown in surface clutter, where radar reflections from waves overpower small returns. The drones are no longer cooperating as a visible formation. They become a 3-dimensional swarm, spread across layers of airspace. From the Russian perspective, tracks appear and disappear. Radar operators see ghost contacts. Thermal imagers show heat flashes that fade before targeting solutions stabilize. Electronic warfare continues blasting into the void, but it no longer matters. The drones are not listening. They do not need instructions. They do not request permission. They simply fly. Each second that passes shortens the distance to Crimea. Each kilometer reduces the number of defensive options remaining. The attack has crossed the point where recall is possible. Only impact or destruction will end it. The Crimean coastline rises out of the darkness like a jagged wall. Cliffs, low hills, and scattered industrial structures break the smooth line between sea and land. Buried among them are radar sites, missile batteries, and gun systems forming Russia's coastal defense belt. On paper, every approach corridor is covered. In reality, coverage is a patchwork stitched together from sensors with different ranges, refresh rates, and blind spots. As the drones cross the shoreline, multiple radars attempt to acquire them at once. Long-range surveillance arrays paint the airspace with high-powered beams. Shorter-range acquisition radars spin rapidly, searching for low-altitude contacts. Fire control radars on Panzer air defense vehicles wait for confirmed tracks before committing weapons, but the system is not facing the direction it expects. After earlier attacks from a different approach axis, several Panzer vehicles have been repositioned to prioritize northern sectors. Their turrets and sensor heads are physically oriented away from the southern coastline. Rotating a Panzer's sensor suite is fast in human terms. It is slow in missile time. 30 seconds are required to slew, stabilize, and reinitialize tracking. 30 seconds is an eternity. The first drone appears inside a radar coverage seam, a narrow overlap gap between 2 surveillance radars, where neither has perfect line of sight at ultra-low altitude. The drone flies through the seam at wave height, its return blending with reflections from rocks, surf, and coastal clutter. A second drone is detected, briefly. The track jumps, range data fluctuates.
the computer struggles to build a stable firing solution. By the time a Panzer's radar locks, the drone has already crossed inside minimum engagement distance. Missiles cannot arm their warheads safely at such close range. The safety logic prevents detonation to avoid self-damage. Guns engage instead. Twin 30mm cannons open fire, throwing streams of high explosive shells toward the target. The fire control computer predicts intercept points, but prediction requires consistent tracking. The drone does not provide consistency. It climbs 10 meters, drops 5, yaws left, rolls right. Each change forces the computer to recalculate. The seconds accumulate. The drone slips through. Another drone climbs deliberately toward a coastal surveillance radar site. The radar is powerful. Hundreds of kilowatts of output energy flood the surrounding airspace. From the drone's perspective, it is a beacon. The aircraft homes in on the emissions. Operators inside the radar shelter watch a small contact approaching on their screens. They cannot shoot it. The radar has no weapons. A missile battery miles away tries to engage, but again the geometry is wrong. The drone passes inside arming distance. At high speed it impacts the radar's rotating antenna. The shaped charge detonates. Molten metal jets through the antenna structure, slicing waveguides, shredding electronics, and snapping support struts. The antenna collapses. Screens go dark. A hole opens in the defensive network. For the remaining drones, the coastline is no longer a wall. It is a doorway. Final strike on Crimean airbase. The last two drones push inland, engines straining as the terrain rises gently beneath them. Fields give way to access roads. Access roads give way to perimeter fencing and floodlit concrete. Ahead, the airbase stretches across the landscape, runways cutting pale lines through the darkness, hangars looming like silent warehouses, and rows of parked aircraft sitting exposed on open aprons. No sirens sound. No warning lights flash. The destruction of the coastal radar has created a dead zone in the sensor network. The remaining Panzer systems attempt to rebuild tracking using secondary radars, but the picture is fragmented. Contacts appear, vanish, and reappear displaced. The drones do not hesitate. One climbs slightly, gaining just enough altitude to clear perimeter obstacles. The other remains low, sliding over fences and service roads. Both navigate using preloaded coordinates. They are not searching. They already know where to go. The first drone lines up on a cluster of parked transport aircraft. Large aluminum airframes reflect faint moonlight. Thin skins, full fuel tanks, a perfect target. At 200 kilometers per hour, the drone begins its terminal dive. There is no evasive maneuver now. No jinking, no climbing, only straight line acceleration toward the aim point. A final burst from a Panzer's cannons erupts from the far side of the field. Tracers streak past the drone, missing by meters. The fire control radar never achieves a stable track long enough to generate accurate lead. The drone hits. The shaped charge detonates on contact. Explosive force focuses forward, driving a jet of molten metal through aluminum, fuel lines, and internal structure. The aircraft's fuselage ruptures. Jet fuel atomizes. The fireball blossoms outward, expanding faster than the eye can follow. 8 seconds later, the second drone arrives. It strikes another parked aircraft from a different angle, compounding the destruction. The pressure wave shatters nearby windows. Burning debris scatters across the apron. Secondary fires ignite equipment, ground vehicles, and stored munitions. Thick black smoke rises hundreds of meters into the air. Inside the airbase, power flickers. Emergency crews scramble, but they are responding to chaos, not preventing it. By morning, satellite imagery shows 2 aircraft reduced to charred wreckage. Dark scorch marks stain the concrete. Debris fields spread outward in overlapping patterns. For Ukraine, the strike is not about the individual aircraft destroyed. It is about demonstrating reach. It is about forcing Russia to spend millions of dollars defending against weapons that cost a fraction of that price. It is about exposing the limits of layered air defense systems built for an era of fast, expensive manned aircraft. Our operation proves that slow, cheap, disposable drones, when used with careful planning and an understanding of physics, can punch through defenses designed to stop cruise missiles and fighters. It signals a shift. Modern air power is no longer defined only by speed, altitude, and payload. It is increasingly defined by numbers, autonomy, and the exploitation of tiny weaknesses. On this night, a handful of small drones rewrite the equation, and the Black Sea becomes a testing ground for the future of warfare.